It's the 7th of April, 2015, and this is episode 202. This show is intended for informational and educational purposes only. What cryptocurrency enables is new, empowering, and exciting, but we're not experts. Just obsessed companions walking the road towards a more peer-to-peer future. Welcome to Let's Talk Bitcoin, the twice-weekly show about the ideas, people, and projects building the new economy and the future of money. My name is Adam B. Levine. On today's show, we ride with LTB correspondent Matthew Zipkin for a discussion about Monero, an alternative blockchain-based token system that aims to solve Bitcoin's privacy problem with ring signatures, for better or worse. They talk origins and features, lessons, attack vectors, and more.
This is Matthew Zipkin, and today on the show we're joined by Riccardo Spagni. He's one of the core developers of Monero. How's it going, Riccardo?
Not too bad in yourself, Matthew.
I'm doing great, thanks. Why don't you give us a little executive summary of what Monero is?
Monero is a cryptocurrency, which is unsurprising. I suppose that's why everyone's listening to this podcast. And it is not based on Bitcoin. So it's not a fork of Bitcoin, and it shares none of Bitcoin's code. Where it differs from Bitcoin is that it is private and untraceable, not only in terms of simple things like stealth addresses, which Bitcoin can do, but also in terms of not being able to tell where funds are coming from.
Great. So Monero attempts to solve the privacy problem with Bitcoin while still preserving the fungibility.
Yeah. There are other things that make Manera special, but that's obviously the big one, and that's the one that a lot of people like to hear about and like to talk about.
Sure. So let's talk about it. So Monero is not a fork of the Satoshi Bitcoin client. It's a fork of something else, right? Why don't you tell us where its origins are?
Sure. So late 2013, there was a white paper, a cryptographic white paper published called CryptoNote version 2. And in it described the cryptography behind Monero. So it described how transactions work and described the proof of work function in Monero. It described all of this, and it had cryptographic proofs at the end. So this was really the model for the cryptocurrency. But there wasn't an implementation that accompanied it at that point in time. The implementation came out later on, and in March 2014 or so, there was this cryptocurrency called Bitcoin that was not so accidentally discovered. And it ended up being this implementation of CryptoNote. Because Bitcoin had this massive ninja mine, Instamine, where 80% of it had already been mined, there was a fresh fork of it, which was Manero. And Monero's code at the point of forking, even though it was forked from Bitcoin, it is the CryptoNote reference code that it was actually based on.
So CryptoNote is basically just a white paper, and Bitcoin is an actual coin. And were either of those projects worked on by any of the Monero developers?
Okay, so CryptoNote is the white paper and the reference implementation. And basically Bitcoin is that reference implementation with like a search and replace to take all the references to CryptoNote as the name of the currency and change it to Bitcoin. So it's a little bit convoluted to try and figure out, but it appears that CryptoNote guy did the cryptography and this reference implementation. And then there was a group that was either semi-related or unrelated that launched Bitcoin or ran with Bitcoin with this massive pre-mine. Monero was initially launched by someone called Thankful for Today, and Thankful for Today also appears to be peripherally related to that group. But because there was some disagreement with some of the things that he tried to force in the community, despite the community saying they didn't want it and even voting for, not to implement it, it ended up being a bit contentious, and there was this community takeover, and he was kind of ousted because he didn't want to play along with what the community wanted. So that's how the Manera core team came to be. And to answer your question, none of the Manera core team members were ever involved in Bitcoin or in CryptoNote until the inception of Monero and the community takeover.
Is CryptoNote an active currency? Are people actually mining it and spending it, or is it just kind of a scientific exploration?
It's a little bit like a scientific exploration because they've got this code up and they've got a little guide to how you can fork it and do your own. And they have a running sort of testbed implementation where you can immediately download it and compile it and connect to some of the nodes. I don't know if they're still running, but they had that for some time. But the idea was that they would reset the blockchain regularly, so it would never hold any value. So it's a little bit like their testnet.
So the stealth and the untraceability that is built into Monero, these are crypto node ideas, and they also exist in Bitcoin. And Monero is another implementation where the main advantage over the first two is that it's a fair distribution.
Yeah, so at the beginning, that was literally Monero's only advantage over Bitcoin or over any other crypto node currency, was that it was just a fair relaunch. Over time, I mean, it's nearly a year now. It'll be a year on April 18th. And over time, we've really started diverging from that initial core code and core protocol. So we're at a point where we are already starting to no longer be based on crypto nodes, but we're starting to be based on Manero because of the amount of underlying changes that have been made.
Okay, cool. So congratulations on reaching escape velocity, I guess. Cool. So that's a great setup. So now why don't we talk about how you achieve the anonymity in Monero that's different from Bitcoin?
Sure. So Manero does two things when we talk about transactional privacy. It has untraceability and unlinkability. So unlinkability is easier to understand. It means that if you've got two transactions and you look at the destination, so in Bitcoin, that would be the addresses that the transactions are going to, it's impossible to prove that they were sent to the same person. Now, in Bitcoin, it's easy because if two transactions have the same address in the outputs for those transactions, then you can say, well, hello, it's the same address. So obviously it's the same person. And with Monero, it's not possible because what happens is instead of it going to an address, it goes to this computed destination. And the destination is calculated by taking the recipient's keys, their public keys, and it does this little hash with some random data, and that's the destination. And the only way to figure out if that transaction is for you to have the private keys for the public keys that you gave to the person and to reverse that. Because obviously without knowing the random data that was padded in there, it's impossible to tell who it's going to. So if you had to take 100 transactions and they were all going to the same person and you looked at them on the blockchain, you would not be able to tell that they were going to the same person because they would appear to go to all of these different addresses or different destinations. So that's unlinkability. Then you have untraceability, which is a different property entirely. And untraceability means that for incoming transactions, you can't tell who's sending it to you because you can get a list of possible senders, but you can't tell which of those possible senders is the real one. So Manera does this through something called ring signatures. And ring signatures are very cool because ring signatures are not like traditional mixing or mixing in any other cryptocurrency where it requires either some sort of centralized point that's going to mix transactions, or it requires semi-distributed group that mixes transactions on your behalf. Instead, with ring signatures, it can be done completely offline. So you don't need to be connected at all as long as you've got a copy of the blockchain. And what it does is it goes and takes a look at the blockchain and it finds old outputs, or they could be relatively new, or they could be from the beginning of blockchain time up until now. And it finds outputs that match your output amount. And then, depending on the mix-in level that you set, it creates this ring or this group of signatures, of which one of the signatures is yours. So one of the signatures is real. The rest are just signatures from before. And it's impossible to tell which of these is the real signature and which of these is the fake signature. Even if that signature of yours is brand new and has never existed before. Because obviously your signature is then going to be used to sign other things later on. So really, it's a fantastic way of being able to deal with transactional privacy, this combination of dual key stealth addressing and ring signatures, because you can't tell who's sending the transactions and you can't tell who's receiving them.
And the ring signatures thing is a very cool, magical math thing that hasn't really been implemented in any other cryptocurrency. So let's talk about that first and then kind of go back to the stealth thing, since we're sort of there on the ring signatures. It's a cryptographic primitive where I think most people who understand Bitcoin understand that they have a private key, which turns into a public key, which turns into an address. And then you use your private key to sign a transaction, and everyone can verify that you signed the transaction by using your public key. So first of all, in Monero, is that type of transaction still valid? Is the elliptic curve public key, private key relationship, is it still the same basic element on that level?
It's the same basic element, but the difference is instead of you publishing a hash of your public key, you actually publish your public key.
And can you send a regular transaction through Monero? Is it possible just to do a regular one-to-one traceable, linkable transaction?
It isn't, in the sense that you can't have a transaction where, without knowing anything else, somebody can look at the blockchain and go, oh, that's where it came from and that's where it's going to. Instead, we have something that's baked into ring signatures and the stealth addresses. We have something called the view key. And the view key is one of the two keys that you have in your wallet. So in Monero, you've got your spend key and your view key. And as you rightly described, Bitcoins, you've got a private and a public version. So in Manera as well, you've got a private version of the spend and view keys, and you've got a public version of the spend and view keys. Now, the view key is very cool because what happens is, if I'm a charity, for example, I can publish my view key on the internet, and anyone can go take that view key and they can scan the blockchain and they can see all of the transactions that I was involved in. So all of the transactions I've received and that I've sent. For charities, it's great. For auditing as well, instead of you needing to try and now sign all of your addresses that have ever been involved in a transaction, you could just give an auditor your view key and say, here we go take a look at this account, go scan the blockchain, go and see all of the transactions I've been involved in. If there are any that you don't know or that are confusing or that are large amounts, then come back and check with me. So it really is great from a regulatory perspective.
So the transparency of a transaction in Monero is actually up to the user, or is it in Bitcoin, anybody can type in your address and see every transaction to your address. In Monero, all the addresses are stealthified, but if you choose to, you can give this other number to an auditor, then your transactions are transparent and they can use that to find your Okay, so the view key is related to the stealth addresses then?
It's primarily related to the stealth addresses, but obviously because it's an integral part of the cryptography, the view key is also used in the ring signatures, just so that it carries through.
Okay, great. So everything's all wrapped up. So I know that the ring signatures is the magic trick here. So what happens is, let me see if I got this right. When you go to sign an output, you take your public key and you find a couple other public keys from the blockchain that could belong to anybody. And you create a signature in which all the public keys are sort of smashed together. So somebody looking at a transaction can tell that one of these public keys signed the transaction, but you can't tell which one it is.
Yes. And it's on a per input basis. So let's say I'm sending 15 Manero to someone. Then typically what would happen is that would require maybe a couple of outputs, because maybe I've got an output of 2 and an output of 3 and an output of 5. It needs to take all of these outputs and use them as inputs in order to have enough in the transaction to satisfy that 15 Manero that I want to send. And then for each of those outputs that are used as inputs in the transaction, it's going to go and get a group of signatures off the blockchain from old outputs, and then it's going to create a ring for each of the inputs. So at best, if you were like a really motivated and really powerful attacker, so we're talking sort of NSA level, like crazy, has access to all the cool toys, and you were able to do something like go and figure out that for this particular input, the 5 people involved with it are, you and me and Bob and Mary and Sue, and you go and strong arm each of us to giving our details, then you could figure out exactly who the real signer is. But you can only figure out who the real signer is for one input. And in a transaction where you've got like 5 or 6 or 10 inputs, it's kind of pointless to just figure out one. It's not enough information.
These inputs that you gather, they're all unspent?
So this is another thing where we differ from Bitcoin. Typically in Bitcoin, you have the sort of global emission at the time, or the number of coins in circulation is easy to calculate. You just take the unspent transaction outputs and you sum them all up and you go, well, at the moment there are however many million Bitcoin in circulation. But as you've just alluded to, With Monero, everything that you sign with an input is unspent because you can never tell if they're actually spent. So even though I might go spend an output today, it'll be used in a ring signature tomorrow. So we don't have unspent transaction outputs. We just have transaction outputs.
Interesting. So you could theoretically, if I was going to create a Monero transaction today, one of the inputs I could use in the ring could be like from your Genesis block. Any transaction that exists anywhere in the blockchain can be used.
Yeah, it doesn't matter how old or how new. And it's impossible to tell if it has really been spent or if it's just being used as part of a ring.
So then I guess, the obvious question that follows is, how do you prevent somebody from reusing the same output over and over and over again and multi-spending that output?
Yeah, because that would kind of, that's the obvious flaw. So there's a special property of ring signatures, and ring signatures are very old crypto. I mean, it's cryptography that first started being theorized in the 80s and early 90s, and this builds on something more recent from 2007 or so. So there's a special property of traceable ring signatures, and the word traceable is misleading because it doesn't mean traceable like you can trace it on the blockchain. But there's this special property of traceable ring signatures, which is something that was developed more recently, and that allows us to have this thing called a key image. And a key image is on a per output basis. So if I create an output today, it can be used for ring signing like indefinitely. But the minute I try and spend that, I create a key image. And that key image now exists. Now, if I try spend it again, even though I'm mixing with a different group, that key image will be the same. So the key image is something that you can't reverse. So it's impossible for an attacker to look at key images and try and extract information from that. But the key image is the special cryptography magic that allows us to make sure that nobody is spending an output more than once.
And the key image, I imagine, also doesn't reveal anything about the sender.
Yeah, doesn't reveal anything about the sender. So it's almost like with a hash of a password. You can't go and reverse that. You have to brute force it or use rainbow tables or some fancy thing like that. But you can't go take a look at a hash and go, yes, this is password 1234. I recognize it.
Gotcha. So a Bitcoin node keeps a database of all the unspent transaction outputs. A Monero node would keep a database of all these key images. And that is its sort of double spend protection.
Yeah, exactly. So that's where on Bitcoin, they use the unspent transaction outputs to verify if the output you're creating has already been spent or not. We use the key images, and then obviously we still have the transaction outputs that we use, but only for ring signatures, not for anything else.
So you mentioned that ring signatures are old technology. So I've got two questions. One is, what other applications are there for ring signatures? Like, why was it developed? And second of all, if it is so old, why do you think Satoshi didn't include it in Bitcoin?
I mean, it was first invented or discovered or introduced, theorized, whatever, in 1991. And the idea was that in its initial release, the idea was that you could have an employee of a large company and they could sign a document, but they could sign it as part of a group. So the whole company, for example, would sign this document. Even though only one person would be doing it, the others wouldn't actively be involved in the signature. And a verifier would be able to take a look at that document and say, yes, this was definitely signed by one of the people that work at this company or one of the board of directors of this company, without being able to tell which particular individual signed it. So there's a lot of application in things like that, in being able to do proxy signatures or being able to sign something on behalf of a group without the group being involved. Because it's not always easy, when you've got, say, for example, a board of directors and half of them are in an airplane most of the time and the other half are scattered around the world, and now you need a document signed urgently. And so they all agree, fine, go ahead, sign it. But, you don't want to have one person signing on behalf of the group, and then it's like, well, did this guy get permission and so on? This is really where it comes into play.
So it's like a secret ballot.
Yeah. So you can't figure out who did the signing. Just you can only verify that somebody in that group did the signing.
Right. And just to follow up, the other members of the group don't have to approve anything. So you could be a Monero user and your public key is just being used in re-signatures till the end of time, and it don't give anybody permission or anything. It doesn't even affect you, but your number is being mixed with other people's numbers.
Yeah, exactly. you could be dead. It could be your life could have ended, and yet your ring signatures live on indefinitely.
So why don't you think this was integrated in Bitcoin?
I think that Satoshi had a lot of really interesting, or not really brand new cryptography, but principles that he brought together in such a special and unique way that to try and layer anything on top of that, or to try and add anything to that, it probably would have broken the principle of simplicity in his mind when he was just trying to get this one thing to work. That being said, he did actually write about group signatures on Bitcoin Talk. There's an interesting post where someone's positing some ideas that could be implemented in Bitcoin. Satoshi replies, and he says that he's actually done some research into group signatures, and that he talks a little bit about that. And that's not to say that Satoshi is at all involved in Monero on any level. It's an interesting find that it is something that he was thinking about a couple of months before he disappeared.
Interesting. So, he could potentially be one of the crypto note people, or who knows?
I hope not, but on the off chance he is. Hey, Satoshi, what's up?
So the untraceability is established by these ring signatures, which mash a bunch of public keys together, and somebody who is looking at the blockchain can say that, yes, somebody from this group has signed this transaction, but you don't know who, and you can tell that an output hasn't been double spent because you're keeping track of these key images. Right away, this is starting to sound like a lot of information, a lot of kilobytes per transaction, right? Because you need to include enough public keys to obscure your actual public key, plus the key image. So how much data is one Monero transaction?
This is obviously a point of contention because Bitcoin already has quite a large blockchain, and no one wants to create a blockchain that's going to be substantially larger, but it is a trade-off. You're going to have a larger blockchain if you are introducing this level of privacy. That being said, we have a smaller scripting system than Bitcoin, or shorter scripting system. So on a pure one-to-one basis, on a like-for-like comparison, our transactions are smaller than Bitcoin. But because of ring signatures, and because ring signatures are used in every transaction, it obviously does lead to increased size. That being said, at the moment, we've actually just posited a minimum amount of ring signatures that can be used for a transaction. And so we're busy adding that in for a hard fork later this year. And the minimum's not very big. The minimum's only going to be 2. And in 2.5 years, it's going to increase to 4. So that's, additional signatures besides yours. The reason that it doesn't have to be massive, you don't need to mix with 50, is because there's this combinatorial effect. In other words, if my transaction has 10 inputs and I am using a mix-in level of 3, then it's my signature plus 3 other signatures for each of those 10 inputs. And so that's a total group of 40 signatures. Even though I'm only using a mix-in of 3, there's 40 signatures to wade through for this transaction. So I don't need to go particularly big in order to get the privacy benefits.
Are you guys struggling with maximum block size limits? There's a debate in Bitcoin about where the max block size limit should be. How do you guys address that?
So we have something in Manero, which is a dynamic block resize system. And the way that works is it has a look back over a group of blocks, typically over a half a day's worth of blocks. And it says, okay, how big have the blocks been? What's the median? And it takes that median, and for the next block that comes in, that block that is allowed, but it's not encouraged that it's above 20% bigger than the median. If it is above 20% bigger, then there's a penalty that hits the block reward. So obviously, from a miner's perspective, they're going to follow that 20% growth rule. They're not going to try and outstrip it. But it can grow pretty big, pretty rapidly. So if we suddenly had this massive influx of all of these users from around the world, millions of them, that suddenly decided today we are using Monero, we could go from our minimum median, which is 20 kilobytes per block. We could get up to 1 megabyte block size limit within, I think when I last calculated it was a couple of days. With no input from us, we don't need to do anything. There will just be a lot of transactions in the mempool. And as the blocks grow and keep pushing above this threshold, then eventually it'll be like, boom, now we're on 1 megabyte blocks. Is everyone happy now?
Interesting. And it's hard for me to think about this on the fly, but does that satisfy the game theory problem that, like in Bitcoin, I believe the argument is something like if the block size were suddenly set to unlimited, then nobody would pay miners fees because there's always be somebody out there to include a zero fee transaction in an unlimited block. So is this a good solution for that?
Yes. So the way it solves it is that the dynamic change in block size is not a permanent change. It's not like we go, well, okay, now we've hit 1 megabyte, and so now that's the new limit, the new minimum median forever. Instead, if suddenly we hit 1 megabyte, but then usage declines and falls off, then that median will go back down. So there's always going to be a desire to include a transaction fee in order to drive miners to mine that transaction. But the other thing, just sort of tangentially to that, to fight the idea of miners caring that much about transaction fees, is we have a very small eternal emission, so a tail emission. So Monero doesn't actually have a limit, a maximum number of coins that will be emitted, but we have a very slightly inflationary model, under 1% a year. And because it's a fixed minimum block reward, once it hits that minimum, it means that the percentage of inflation will decline over time. And the idea is that alone will encourage or will maintain mining incentives forever. So we will never need to rely on fees for mining incentives. And we can thus have a real fee market and competition between transactions and transaction fees, without having to worry about are miners going to bother mining.
So if that's the case, then why do you need block limit at all?
The block limit comes in because you want to, whilst you've got the tail emission that's going to encourage mining forever, you also don't want to allow for blockchain spam. So you want to encourage growth that is manageable. And not to put too fine a point on it, but at this point in time, the Manera blockchain is bigger than the Bitcoin equivalent. Our raw blockchain is about 2.5 gigabytes after a year. And that's obviously going to get bigger with time. So we don't want to get to a point where we're rushing ahead of technology, where we are outpacing the laws that govern disk density and that sort of thing. So the block size limit, even though it's dynamic and it can grow quickly, it still makes sure that miners aren't just shoving everything into a block and then suddenly there's this massive block and then there's a small block. And we've got to write code that has to deal with these massive changes and massive shifts. Instead, we can just let things grow over time as we hope they naturally will.
Interesting. So is there an attack vector in which somebody can keep creating transactions and build the block size upwards and sort of affect that network variable?
Yeah, that has actually been done already. We had an attack in September last year. And in order for them to perform the attack, they needed to have more than 512 transactions in a block. And so they had to grow the median from its minimum of 20 kilobytes to 72 odd kilobytes in order to jam these 514 transactions that they had in the block, to trip a buggy piece of code that calculated transaction hashes above transaction number 512 in a block. And obviously that's long since patched. But they were able to grow the block size limit relatively rapidly, but it cost them in fees, especially because at the time we had a per transaction fee of 0.1 Manero, which we'd raised because we'd seen them trying their attack a week before. And so we rolled out a sort of emergency hard fork to raise the fees to try and prevent them from doing this. And they just sucked those fees up. They were determined. And they managed to roll out enough transactions to get the block size limit up to enough where they could jam these 514 transactions in a block.
So they knew that transactions 513 and 514 wouldn't be verified or something, or could be double spent somehow or something like that?
It's not that they could be double spent, but what would happen is the hash that was computed for those two transactions by the mining node for the pool that mined them could not be verified. So because it was basically what happened is for transactions 513 and 514, when it computed the hash, it spilled over into uninitialized memory. And so it had this hash that if I try to verify it using the old code, I would also spill over into unverified memory, and I'd go, well, the hash that I get is different. It caused a fork, and it's the only fork we've had thus far. The network forked for 30 minutes before the fork was resolved. And we had to actually put in a piece of code that now forces a hash over the entire blob, so the raw block, not just over the block header, for that one naughty block.
Man, that's amazing. Cryptocurrency is just such a brutal environment, huh? It's just like taking something delicate like a flower and you just drop into this big vat of acid. That's intense.
It is an incredibly sophisticated attack. So it really does go to show that if you are designing or working on a cryptocurrency, you absolutely cannot eschew cryptography. You've got to know what you're doing, and you've got to understand cryptography to quite a decent level to be able to stop that sort of thing from happening.
So in this case, the hard fork resolved itself the way the software was designed to, as in a longer chain emerged.
And everyone sort of eventually aligned to that longer chain.
I see. So you didn't need a hard fork to solve this problem, but since then you've added, what did you hard code that 514 transaction?
Yeah, we've hard coded that hash for the blob, so for the raw block. The reason being that there were a couple of nodes that were stuck on a subchain, and they refused to see the long chain as long because they couldn't verify that transaction for the long chain. So they said, yes, there's a longer chain, but because I can't verify this particular transaction in the longer chain, I'm going to ignore it. And I believe I'm on the longer chain, even though I'm not receiving any transactions for it or any blocks. So we had to write code to help those guys, firstly, so that when it started up with the new code, it would roll back to the transaction on their local blockchain, and it would go, oh, I don't match the raw block hash for this particular block, and so I'm going to open myself up to the network and receive that block until I get the one that matches this block hash.
So was the solution just to fix the 512 cap so you can have more transactions, or are the block hashes now including more information, or...
There wasn't a cap, but there was just a very, very small mistake, a bug in a very tiny piece of C code that is used to compute the tree of hashes in a block. And that was fine for the first 512 transactions, but any transactions thereafter it would have tripped up on. So the solution was to fix that piece of code and then to put in a checkpoint for that one block that was based on the old code, so that we forced a particular hash network-wide for that just that one block.
Was the attacker able to double spend or earn any money?
They weren't able to do anything because the fork resolved itself so quickly, and also because we were watching it at the time, and the Bitcoin talk thread, if you go back to like September 4th to 7th, or a little bit before then, beginning of September to September 7th, it's fascinating to read because we were like on alert, and we were all posting the whole time like, okay, this weird thing is happening. We don't know why it's happening. Okay, now we've done this. Okay, now, we're still not 100% sure why the attacker is, or why somebody's growing the limit. It's not normal usage. And the minute the attack took place, we reached out to all of the exchanges and we told them to suspend deposits and withdrawals until we were able to fix this. And obviously, if we had had a much wider reach and we had been in, thousands of merchants, that would have been a lot more difficult. But the attacker wouldn't have been able to do much except send transactions to that broken subchain and to the main chain and hope that a merchant was on the one or the other, and then try and convince the merchant to give them some digital download. And they'd have to have done that within the space of a few hours before the merchant cottoned on to the fact that something was wrong.
Amazing. Well, kudos to you and your team for being responsible developers and alerting everybody when there's an emergency.
Today's episode of Let's Talk Bitcoin is brought to you by the LTB Companion Wallet, which I'm really pleased to announce is available right now in the Chrome store. If you've never gotten around to setting yourself up with a counter wallet so you can receive your share of LTB rewards, this is the kinder, easier, and more convenient way you've been waiting for. To get your free LTB Companion multi-token wallet, visit letstalkbitcoin.com and follow the link. It's pretty obvious. Once it's set up, visit your letstalkbitcoin.com dashboard where you can enter your compatible address and add it to your account using the address verifier. That's all you need to do to start earning LTB coin rewards, except of course use the site. You'll receive LTB coin for every comment or forum post you leave, the upvotes you receive, new articles you visit, and of course our flagship Magic Words program. The Magic Words program tries to solve the problem of tracking how many people actually listen to the show all the way through. During each episode, I'll say a specific word, and listeners like you have 7 days to visit their account on letstalkbitcoin.com or to use the Magic Words interface within our iOS application and enter that word, proving that not only did you listen, but that you're keeping up to date. Of all the activities that can earn you rewards, entering Magic Words is the most highly valued. Speaking of Magic Words, for today, that'd be Ring. That's R-I-N-G, Ring. You've got until the 14th of April to visit letstalkbitcoin.com or the Let's Talk Bitcoin iOS app to enter it for your share of the listener rewards.
Curious if you've done any innovation on the mining algorithm or the block time target?
Let's talk about the block time target first. The block time target that Thankful for Today set was 1 minute, which is, it's low and it's not ideal based on the current level of technology and the current sort of latency across the world when it comes to internet connectivity. And that having been said, latency is improving. So whilst it is something that we are looking to change at some point, it's not something that we are necessarily going to change if technology can catch up with us fast enough. But if we did have to change it from 1 minute, we could change it to 2 minutes or 4 minutes and then obviously adjust the block reward accordingly, which would be quite simple because you're doubling it up or quadrupling it. But it would be with the idea of reducing the number of orphan blocks that are created. And it's not like there's tons of orphans, but it is something that's it's simply not ideal. And I have no idea what his rationale was for choosing a 1 minute block time, but obviously he thought it was cool.
Yeah, this comes up a lot with altcoins that have shorter block times in Bitcoin. And it kind of makes me wonder, like, I guess if you have too short of a block time, you're definitely going to have more orphans. Do you still effectively have to wait 60 minutes in real world time before you're confident something can't be double spent? You know, what is the trade-off, and like, why is the Bitcoin block time 10 minutes if 1 minute would work and you just have all these orphans? But you know what I mean?
There's actually an interesting paper by Manny Rosenfeld, and I emailed Manny and we've chatted a little bit about block time and orphans and hash rate based double spending and that sort of thing. And he has this really interesting conclusion, which is that the risk of double spending decreases not based on real world time, but based on the number of successive blocks. So there's this interesting side effect to altcoins that have a lower block time, that they can actually have reasonable confirmation security within a smaller real world time than Bitcoin. That having been said, you then have the other side of the coin, which is the increased number of orphans and the fact that 99.9% of all cryptocurrencies out there, pretty much all of them except for Bitcoin, could trivially be attacked by a very motivated attacker with a lot of money that could buy up a lot of hash rate. So the protection doesn't really come into play with any cryptocurrency besides Bitcoin.
I see. So a lower block time is actually a vulnerability unless you have the massive mining energy that exists in Bitcoin.
Yeah. If you're not Bitcoin, then having a 1 minute block time or a 10 minute block time or a 2 minute block time is all inconsequential because, and I mean, I'm obviously using it in relative terms because I think that most altcoins are so disinteresting to attackers that they wouldn't go and spend the money on attacking it anyway. But if an altcoin had to rise to a sufficiently large level and it didn't have a sufficiently large mining network, it would be at a very great risk to a motivated attacker with a lot of money.
I saw recently a comment from Mike Hearn who said that Satoshi originally picked a 10-minute block time because the amount of time it takes for a global consensus is about a minute. And so Satoshi thought that 10% of lost mining work was like a fair amount. To which Mike Hearn also added that the global consensus time is actually around 25 seconds currently. So Satoshi was pretty close, but it seems like Satoshi's goal was to not waste mining energy, or to waste 10% is his tolerable amount of wasted.
Yeah, because I mean, you do the more orphans you have, the more wastage you have. And if you are burning up whatever, say 30 or 40% of your electricity on that, then how beneficial is your proof of work?
Right. Is there any innovation in CryptoNote, Monero on the proof of work, or is it SHA-256?
So it's not SHA-256, and it's another algorithm. It's an algorithm that the CryptoNote white paper doesn't describe in very much detail. It has like a couple of bullet points to describe what they want to achieve, and then the rest is left up to the actual implementation. And basically, it does a couple of things to be memory hard and to design how the scratchpad is designed and so on. And its aim is to reduce the performance gap between CPUs, GPUs, and ASICs. So it's not to reject ASICs, and it's not to be ASIC proof, because that's impossible. But the idea is when ASICs arrive, and if Manero is ever, or if it ever lasts long enough, and if it is ever worthwhile, there will be ASICs. When those ASICs arrive, can you still GPU and CPU mine? And with the CryptoNote proof of work, you can. So that's really the aim. Now, because it has this reduced performance gap between CPU, GPU, and ASIC mining, we've got this thing that we've developed that we're busy building out at the moment called smart mining. And smart mining is a function that will be designed to be sort of like Boink or SETI at home. So when you fire up your wallet for the first time, it's going to say to you, would you like to enable smart mining? It's going to be ticked by default. It's going to explain what it is. And if you enable smart mining, then in the background, when you are not using your computer, so when the CPU load is way down, and when you're not on battery power, if it's a laptop, then it'll start mining. And it will mine to a threshold, so it's not going to like use 100% of your CPU and degrade its life, but it will mine in the background quietly to a threshold, either to your address or to the developer donation address if you so choose. And the idea is that instead of there being a cabal of miners or cabal of mining pools, if we have sufficient usage of Monero and there are a sufficient number of people that enable smart mining, then hey, there's no need for pools to exist, or there's less of a need for pools to exist, because there are all these people that are solo mining to support the network, or they're P2 pool mining to support the network. And they don't really do it because they're earning income. They do it just because it's this thing that they left the box ticked and off it goes in the background.
What's the mining algorithm called?
So the mining algorithm is called CryptoNite. So like crypto and then NITE or NIGHT, depending on where you read it. And the performance gap or the efficiency gap is really not bad. So basically, from an efficiency perspective, in other words, how efficient is it from an electricity perspective? GPU mining is between sort of 3 and 4 times more efficient than CPU mining. And we expect that a well-designed ASIC will be probably another 3 to 5 times more efficient than that.
But still not leaving CPUs in the dust.
Yeah, so you're not going to, I think by the time ASICs come out, you're not going to be profitable with CPU mining. So it's not going to be the sort of thing where you're going to have banks of computers that are grinding away on their CPU. But if you leave smart mining on in the background, it's like neither here nor there. Maybe you get a couple of cents, maybe you don't. And it will mean that GPU miners won't be left in the dust specifically. And they'll be able to, the sort of pro GPU miners or the more organized GPU miners will be able to GPU mine well into the release of quite efficient ASICs.
So I kind of want to go back actually. So we started talking about the untraceability with the ring signatures and then went off about the blockchain and stuff like that. But there's one thing we didn't dwell on, which is the stealth addresses.
Yes.
So could you explain how a stealth address works? What does the user have? What does the user give out? And how does the user know when he or she has actually received a transaction?
What happens is, if you've ever used Manero, you'll have noticed that your Manero address is long, like stupidly long, like scary long compared to a Bitcoin address. And it's because it's got 2 public keys in there, your public view key and your public spend key. And what happens is, if I want to send a Manero transaction to you, the way I compute the destination for each output, and there could be, bearing in mind, there could be multiple outputs going to you, so I'll repeat this process for each, is I perform a Diffie-Hellman key exchange over those 2 keys with my keys, And then there's a little formula that it gets plugged into. And basically it takes a hash of the one key multiplied by this base point, and it adds the other key, and it's got some random data that it packs into there. And because of the random data, it means that even though these multiple outputs are going to you, they appear to be different. They appear to be going to different destinations. Now, that's what the sort of process for sending. Now, the process for receiving, and obviously this is all stuff that's invisible to the user. The process for receiving is I go and I take this transaction. It's got a number of outputs. And for each of the outputs, I go and I run a little computation over each output. And basically it takes the private key, the private view key, and the private spend key that I have, and I plug it in against this destination, and what comes out of that is, oh, hey, this transaction is for you, because I'm able to recognize it as being for you, even though there's this random data around the function that hashed your key and so on. And because there's this recognition, I'm then able to take that and add it into my wallet as an output that I can now spend because I've received it. Now, the really cool thing about this is because the computation happens over every single output, if you're on a low power device, like let's say you're on a mobile phone, you don't actually need to do that. You can run a Manero node at home or wherever it is, and you can pass the processing of transactions back to that node. And it can just say, oh, hey, hello, mobile device, you've got a new output. Here are the details. It's a way of being able to offload the processing as well without needing to do the processing on that device.
So it sounds sort of like an SPV process.
That offloading is a little bit like an SPV process, but in an ideal world, you'd be running the node yourself because you don't want to trust somebody else to do the processing for you because you've got to give your view key to them.
Right. So you'd be giving up privacy.
Yeah. I mean, it's okay. It's not terrible to give up a little bit of privacy for something like that, but ideally you don't want to. So one of the things that we're looking at the moment is a way to do that better. So we're looking at doing things like, is it possible for us to pass a Bloom filter of sorts that allows a node to check a group of transactions against a group of view keys that you express interest in without knowing which of those particular view keys you are interested in, which is basically the way SPV works at the moment. If you sort of bounce that around between nodes, then you can receive all of the transactions that are for you with some false positives, and those nodes will never know what your actual view key is.
Cool. So the deal with stealth transactions, I just want to make sure I got this right, is you give out, so you give a public key, and then I take that with my private key and create a shared secret. And then when I send you my public key, you compare it with your private key, and you can derive the same shared secret. So this is the Diffie-Hellman process, right?
That's the Diffie-Hellman, yeah.
You got public and private. I got public and private. By only exchanging public keys, we are able to independently arrive at a shared secret, which we can then use to communicate.
Yeah.
Okay. And so why is the view key necessary?
Well, that Diffie-Hellman exchange happens just so that we've got a shared secret. It's not related to anything except to for us to get a shared secret so that I can effectively encode the transaction output so that you can decode it. Without that shared secret, it's difficult for you to unpack the transaction. So the idea being that both of those keys are there, but the Diffie-Hellman exchange allows us to make sure that the recipient can very easily verify which transactions are his without needing to know his spend key even.
So when you're looking at a Monero transaction, let's say on a block explorer, is it the destination address of the transaction that is basically encrypted with this process?
Yeah. So, I mean, encrypted's kind of the wrong term, but basically the easiest way to understand it is if I'm making a payment to someone whose public keys consist of A and B, then what I do is I take this random thing, and let's call this random thing F, and I go A and B and F. That's the destination. But then I hash the whole thing. So as far as anyone can see, the destination is some hash. And then if I'm sending another transaction or within that same transaction, another output to the same person, I'm going to go A and B and Z. And now I hash that. Now it's a different hash, even though it's going to the same person. So that's obviously like incredibly oversimplified, but it gives you the idea that that random thing or the random number that we're using for the calculation is the thing that makes it completely impossible to figure out unless you are the actual recipient.
I see. So because there's an irreversible hash, you can give out your address and nobody will be able to find any transactions to that address because essentially all the transaction destinations are hashed.
Yes.
But if you know the address, which you do because it's you, then you can hash yourself. And when you see a hash that matches your hash, you know you've got a transaction incoming.
Yes. And because of Diffie-Hellman, you don't actually use the address to decode it. You use your private keys. So the shared secret is actually the clever thing in there. So in other words, leaking your address, like, I mean, I can go put my address out in the open on a blog or on the internet and I don't care because no one can use it. They can't use it to figure out which transactions are mine. They can't, there's no Monero rich list, you know, you can't do any of that with Monero.
Interesting. But so now you've got this other component called a view key, which it sounds like is sort of a trap door that will allow somebody to find all the transactions to your address if you let them.
Yes. You know, the sort of knee-jerk reaction might be, oh, but, you know, the view key, all you need to do is get the guy's view key. But how? It's a 256-bit key. Short of rubber hose cryptanalysis, which is where you beat the guy with a rubber hose till he gives you his view key, there's no way for you to magically figure it out without using the power in the universe for the next several gajillion years until the universe dies. Then you can figure it out.
So if you're a Monero user and your privacy is important, you keep your view keys just as private as your private keys. You keep them encrypted and you keep them safe and offline and all that kind of stuff.
Yeah, absolutely.
But if you want to be able to prove to the world exactly how much money you have for whatever reason, like you said, you're a charity, then you can disclose your view key and everybody can scan the blockchain and see everything.
Yeah.
Can they see what you're spending or just what you've earned?
They can see what you have received and what you've spent. Obviously, seeing what you're spending doesn't help them see what you're spending it on unless they can deduce based on where it's gone to. But all they can see, again, on the blockchain is they see the stealth address has gone to. So without the participation of the person you're paying, they won't be able to suck any information out of that beyond you made a payment of X to this destination.
That's because with somebody's view key and their public key, you can tell which outputs they own. And because of the key image database, you can tell which of those outputs have been spent already. But because of the ring signatures, you can't see where those outputs have been spent to.
The stealth addresses stop you from being able to see where they've been spent to. The ring signatures stop you from seeing where they've come from.
Oh, okay, right.
So if I earn a salary once a month of 100 Monero, you will, using the view key, see the 100 Manera come in every month, but you won't be able to tell who's paying me.
Right, okay. But the bottom line is, with somebody's view key, you can see what their account balance is. You can see all the transactions they've received, and you can see which of those transactions they have spent, but you can't tell where they're coming in from or where they're going out to.
Yes. I mean, you can see, like, exactly, okay, I received 100, I spent 50 on a thing, but without going and finding out where I spent the 50, either from me or from the person who I paid, you're not going to know what it is. So this has great advantage in many things. For example, if you are a company and you've got a group of accountants or bookkeepers that keep your books, but you don't want them to be able to spend any of the funds, they would be able to have the view keys to all of the company's accounts and to see all of the transactions flowing in and out and record them and make notes and whatnot. But they wouldn't be able to spend them. And then maybe the spending requires spend keys that are under the control of the managing director or the CEO or whatever it is. So it allows more fine-grained control because you can say, I want these people to see it and not everyone else. Or maybe a simpler example, you're a parent, you've got a child. Your child has, in this hypothetical future where Manero is amazing and accepted everywhere, your child has a Manero wallet and off they go and they spend Manero on stuff. And as a parent, you've got the view key. You can't like go and spend your child's pocket money, but you can see that they're spending it like really fast on stuff. And you can go and talk to them and be like, well, what did you spend so much money on?
I might have missed this, but the stealth address contains your public key and your view key?
No, you're right. The stealth address or the address that you publish contains both the public version of your view key and your spend key.
Oh, okay. Okay, so it's the public version of your view key. So you can't use the public version of the view key to do all the stuff you're talking about. Okay,
only the private one.
Right, but the public version of the view key is necessary to make all the math work.
Yes.
in the end when you do decide to, okay, I see. Okay, that's a great technical overview. It seems like you've got some really very cool high-tech stuff happening. Are there any other cool features of Monero or CryptoNote even that you think are intriguing?
We've spoken about a lot of the core things. There's some other cool stuff that we're doing in future, and some of the cool things that we're doing right now. We have a system that we've developed, or a standard that we developed, called Open Alias. And Open Alias we initially developed for Monero because, the stealth addresses kind of made it okay. But it's something that we have that allows, or that works with any cryptocurrency, including Bitcoin. And the idea is that instead of making a payment to very long address, whether it is very long Bitcoin address or very long Manero address, you can make a payment to something like donations@getmonero.org or rick.spunny.net. And what OpenAlias does is it goes and it does a little DNS lookup for the TXT record on that. And then it gets this little bit of data back. And based on that record, it's able to say, oh, okay, here's the address the actual address that I need to pay. And that is available the paying component is available in Electrum 2.0 and obviously in the Monero core and in the MyMonero web wallet and also in the coin.space web wallet. All of those support OpenAlias for Bitcoin or for Monero.
Is it decentralized?
So it supports both. So if you have a domain and you want to use a domain that you already own, great, go ahead. If you have a bunch of domains, do it on all your domains. If, however, you want to use something that doesn't require that you trust ICANN or whatever country owns that top-level domain, then the standard is simple enough that it works with Namecoin, with Diana, with PTP DNS, so any of the distributed DNS systems. And in fact, we provide a list of OpenAlias compatible resolvers that don't log your requests, that support DNS crypt for private resolution, and that support Namecoin as well as normal DNS resolution. So we're trying to provide both options, both the decentralized, disconnected stuff, and then the thing that is like really easy to get on to really quickly, which is your normal domain name stuff.
And what about the rest of your infrastructure and community? How are you guys doing on mobile apps and merchant adoption and things like that?
So it is a bit tricky because of the fact that Monero is not based on Bitcoin's code. So we don't have like 5 years of incredible development where we can sit back and go, well, Bitcoin's done all of this for us, so we're just going to soak up the benefits, which makes it very challenging for merchants and for us. So we have a web wallet. It's not owned directly by the core team, but I operate it. And one of the Monero community members helped me get it up and running from a finance perspective. And it's at mymonero.com. And it really is the easiest way to get to start using Monero. It works on mobile, so it works on iOS, Android, BlackBerry 10, and Windows Phone, and pretty much anything where you have a browser that supports modern JavaScript. And obviously it is a web-based client, so all the normal caveats apply. But one of the cool things about it is that you're only ever passing your view key to us. So MyMonero, again, can tell what your transactions are, but we can never spend the funds on your behalf. It's impossible. So that's the easiest way to get to get on board and to get using Monero on a mobile device, on a desktop device, on anything. Merchant adoption is a little bit more challenging, but there's a really cool service that launched a little while ago, and that is XMR.2, so XMR.to. And XMR.2 allows you to say that you want to pay a Bitcoin address, however many Bitcoin, and then it pops up a little thing and it says, okay, that'll be 100 Monero, and please pay 100 Monero to this Monero address with this payment ID. And you go make the payment with Monero, and then they go and do the Bitcoin payment on your behalf. And the cool thing is they don't go and then do a trade on the market for that amount immediately. They go and do the trades on the market trades on a regular basis, once a day, once a week, whatever it is. So there's no sort of connection that anyone can make between market trades and the payment. I mean, they're sort of like the dead link between the Bitcoin address you requested to be paid and your Monero payment. And obviously, because no one can look at the blockchain and see where the Monero payment came from, you're pretty safe.
You know, one other thing I thought of, I noticed in the CryptoNote white paper that it uses a different elliptic curve than Bitcoin.
Yes.
That stood out to me. Why is that?
Bitcoin's elliptic curve choice, again, not their choice. It's something that Satoshi chose. And there's nothing fundamentally wrong with the elliptic curve that they've chosen. And ZEP-C 256K is fine. You know, you can't fault it, except that there are, like, people like Daniel J. Bernstein have got, you know, little things that they say, oh, there's this problem with that, with that curve, and there's that problem with that curve. But I think when you're playing on that level of cryptography, I'm not 100% sure if the problems they identify are really problems. So by chance and careful planning, the CryptoNote guys chose ED25519, which is a Daniel J. Bernstein curve, and curve 25519 is part of the EDDSA signature system. And like ED25519 is actually pretty cool because it's generally considered to be quite safe. It's used in things like DNS Curve and DNS Crypt. It's used for OpenSSH. It's used for all of Apple's encryption, their communication systems for iCloud and for I can never remember the name of it. But I mean, it's used quite extensively by Apple. What else is it? Oh, it's used by Tor.
Okay.
So basically the curve that we use, I mean, if it's trusted by OpenSSH and Tor and we should be okay.
Interesting. Yeah, because I think Bitcoin's curve, correct me if I'm wrong, is actually not used by anybody. And Satoshi picked one that was kind of new. I
really do think, like, when you're playing in that level where you're debating curves and whether SecP 256K1 is a safe curve, I don't know. I'm not 100% convinced that you can make an argument either way. There's a debate about SecP 256K1 versus SecP 256R1, and because they're closely related, and whether the one is better than the other. And there are a couple of sporadic quotes about Satoshi choosing SecP 256K1 because he felt he had an inclination that SecP 256R1 was a honeypot, or was compromised on some level. But I mean, like, really, to compromise an elliptic curve vulnerabilities are like that, you know, we're really getting into the realm of theoretical cryptography, where I don't doubt it's possible and I don't doubt that it's been done. But I think that it is incredibly, incredibly difficult to do. And I think even an attacker on the level of like the NSA and, you know, the people that we're all supposed to be terribly scared of, I think that they have much bigger fish to fry than compromising an elliptic curve.
Sure. I just thought that was interesting in the white paper. It is definitely the tweakiest of all tweaky possible.
Yeah, it is. It is. Look, it's hella interesting, and it's Daniel J. Bernstein and I forget the other guy's name. They've got a website called Safe Curves, and Safe Curves basically lists their ideal, or their overview of which curves are good and which curves are bad. And they list SecP 256K1 as bad for a number of reasons, which are, quite frankly, beyond my realm of knowledge and understanding.
Sure. Well, thanks for talking to us, Riccardo. Is there anything else you want to add, or do you guys need developers? What are you looking for?
Well, look, I mean, we've got a lot of cool stuff that we're doing. We have a group of academics and cryptographic researchers that obviously the core team is part of, and then a number of PhD candidates and qualified cryptographers are part of, and that's called the Manera Research Lab. So anyone who's particularly interested in the cryptography behind Manero and who wants to help us on future research projects, then they can definitely reach out to us. And also, anyone who wants to contribute to Manero Core or to any of the peripheral projects, the easiest way to get in touch with us is either on IRC, we're on Freenode, in #Manero-dev, or our website is getmanero.org, and our email address is dev@getmanero.org. So reach out to us and say you want to get involved. And anyone who wants to get involved in any other way, whether it is, whether you can't contribute directly, like contribute code or anything like that, then please do feel free to donate or sponsor. We have a couple of, or a number of really cool sponsors that have sponsored some of our hosting and some of our firewall appliance stuff and some of the software packages we used. So yeah, pretty much any help was greatly appreciated.
Great. Riccardo, thanks so much for your time.
And thank you very much for having me, Matthew.
Thanks for listening to this episode of Let's Talk Bitcoin. This episode was sponsored by the LTB Companion multi-token wallet. It's counter-wallet compatible, free like speech and like beer, and available now at letstalkbitcoin.com. Content for today's episode was provided by Matthew and Riccardo. Music for today's episode was provided by Jared Rubens and General Fuzz. This episode was edited by Matthew Zipkin and Adam B. Levine. Any questions or comments? Email Adam at letstalkbitcoin.com. See you next time.